Have you ever really thought about how the world around you gets built? I mean, from the smartphone in your hand to the car driving down the street, it all follows this incredibly precise, almost hidden blueprint. Today, we're going to decode that blueprint. We're going from a single atom all the way to a fully automated factory. So let's start by stepping right onto the factory floor.
Okay, at first glance, a modern factory floor, it just looks like chaos. You know, a total whirlwind of robotic arms, moving parts, sparks flying. It's a lot. But, and this is the key, there is a deep underlying order to everything you see here. Because out of all that apparent chaos, we get products made with microscopic precision. I mean, every single one is a perfect, identical copy of the last. So how? How do they do it? Well, the story starts smaller than you can possibly imagine. To really get how anything is made, you first have to understand what it's made of. We've got to go all the way down to the atomic level, to what you could call the very DNA of the material itself. It all kicks off with something called the atomic packing factor, or APF. Just think of it like this. How tightly can you pack a bunch of oranges into a box? Well, the way atoms arrange themselves in a crystal structure determines literally everything. A material's density, its strength, its fundamental nature. It's the first and most crucial design choice, deciding if a material is going to be light and flexible or super dense and strong, long before it ever even takes a shape. So how do we actually use that atomic knowledge? Okay, this is where it gets really fascinating. This chart right here, the iron-carbon diagram, it's like the ultimate cookbook for steel. See all those different zones and lines? By precisely controlling just two things, the temperature and the tiny amount of carbon you mix in, you can create completely different types of steel. Down here, you might get something tough and structural, but way up here, you get something hard but brittle, like cast iron. It's basically a treasure map for creating the perfect material for any job you can think of. All right, so we've designed our material at the atomic level. Perfect. Now, how do we give it a shape? Well, the first and probably most ancient method is to just melt it down and pour it. This process is called casting, and the idea behind it is just beautifully simple. You create a cavity, a mold, in the exact shape you want, you pour in the liquid metal, and then you just let it cool down and harden. Seriously, think of it like a high-tech, super hot Jell-O mold. It's the absolute best way to create really intricate, complex shapes all in one go, like, say, the engine block for a car. But what if you don't want to melt the metal? Well, you can reshape it while it's still solid, just by using immense pressure. This is called metal forming. And processes like rolling, which you see here, are kind of like using a giant industrial-sized rolling pin to squeeze a big block of metal into a perfectly thin, uniform sheet. And you can do this either hot or cold. Hot working is a lot like shaping warm clay. The metal is soft and pliable, so it's easy to make really big changes to its shape. But the real magic happens with cold working. When you reshape the metal at room temperature, it actually forces the crystals inside to realign. And that makes the material significantly stronger and harder. It's a process called strain hardening, and it's exactly how we get those high-strength precision panels for something like a jet fuselage. Pretty cool, right? Okay, so we designed our material, and we've shaped our individual parts. The next logical step, of course, is to join them all together. And this is where the magic of welding comes into play. At its core, welding is basically creating a tiny, controlled lightning bolt. An electric arc jumps across the gap, creating this superheated plasma bridge between the welding electrode and the metal. That intense heat melts the edges of the two pieces along with some filler material from the rod, and they all flow together, becoming one single, solid piece when they cool down. And you know that coating on the outside of the welding rod? That's not just for show. It's a chemical powerhouse. As it burns, it releases a gas that shields the molten metal from the air. It helps stabilize that electric arc, and it creates this layer of what's called slag that actually pulls impurities out of the weld. So that coating is absolutely crucial for making sure you get a strong, clean joint. All right, let's switch gears a bit. We've talked about the hands-on processes. Now let's get into the brains of the operation. How do we get machines to do all this work for us with, superhuman precision? Well, we have to teach them a language. That language is all powered by what's called computer numerical control, or CNC. This is the brain of modern manufacturing. It's actually pretty simple. CNC takes a digital design from a computer and translates it into a super precise set of instructions. Then a machine, could be a lathe, a mill, a robotic arm, whatever, can follow those instructions perfectly 1,000 times in a row, and it will never, ever get tired. Now, the instructions themselves, they're written in a language called G-code, and I know it can look like some kind of cryptic alien script, but the commands are actually really simple. For example, G01 is one of the most common ones. All it means is, hey machine, move in a perfectly straight line from where you are now to the next coordinates I give you. That's it. A really complex design is just built up from thousands and thousands of these simple, logical movements. So how does that line of code become a physical action? This diagram shows the whole chain of command. The computer sends out this rapid series of electrical signals, a pulse train, to that stepping motor. Each tiny little pulse tells the motor to turn just a precise, microscopic amount. And as you can see, that motor turns a lead screw, which moves the whole work table back and forth. Thousands of these pulses every second translate directly into the smooth, perfect, and incredibly precise movements of the machine. So, we've gone from atoms to parts, and from parts to machines. Now, let's zoom out one last time and see how the entire factory is orchestrated. How does a company even decide what to make and when to make it? Well, it all follows a master plan. It starts with forecasting, trying to predict customer demand. That forecast then feeds into what's called aggregate planning, which is all about balancing your resources. From there, you get a master production schedule that says exactly what to build and when. And finally, that schedule drives the material requirements planning, which is a system that automatically figures out every single nut, bolt, and piece of raw material you need to get the job done. See, the modern factory needs to be more than just powerful. It has to be smart and adaptable. And that's the whole idea behind a flexible manufacturing system, or FMS. You can think of it as soft automation. It uses this whole network of CNC machines and robotic handlers that can all be reprogrammed really quickly. This lets a single production line switch from making, phone cases one day to car parts the next, with almost no downtime. It's incredibly efficient. And this chart really shows you where FMS shines. On the far left, you have that rigid, hard automation that's perfect for mass production, like making millions of identical soda cans. Way over on the right, you have custom, one-off jobs. FMS absolutely owns this middle ground, batch production. It gives you all the efficiency of automation, but with the crucial flexibility to adapt to new designs or smaller production runs. So there it is, the complete journey. We started with the specific arrangement of atoms to create the perfect alloy. Then we shaped it, we joined it, we taught a machine a special language to build with it, and we orchestrated an entire factory to manage the whole process. It's an incredible symphony of physics, chemistry, and pure information. It's the hidden blueprint that turns raw ideas into our physical reality. Now that you've seen how it all works, will you ever look at the objects all around you the same way again?